Many institutions and teaching environments do not have access to parallel platforms for parallel and distributed computing education. Teaching key concepts such as speed-up, efficiency, and load balancing are much more effectively done on a parallel platform, particularly since these will soon be the only available computers. Fundamentally, LittleFe can be used to teach all kinds of parallel programming, and can be used to develop and test code to be run on production machines. It is useful for CS courses with programming components. LittleFe is a complete 6-node Beowulf-style portable computational cluster, which weighs less than 50 pounds, easily and safely travels via checked baggage on airlines, and sets up in under 10 minutes. All you need is a wall for projecting an image and a standard electrical outlet. By leveraging the Bootable Cluster CD project and its associated curriculum modules, LittleFe makes it possible to have a powerful, ready-to-run computational science and high-performance computing educational platform for less than $2,500. The name LittleFe is a play on words. The world's highest performance computer centers contain multi-million-dollar computers, affectionately referred to as Big Iron. LittleFe seemed an appropriate name to describe a small, inexpensive cluster. A current written form of these instructions are available on the site http://littlefe.net. Let's do a quick overview of where we are headed. This video presumes you have a box of parts on a table in front of you. The information in this video will help you successfully transform this into a fully working LittleFe cluster. The 3 builders are each responsible for a different part of the build. It turns out the 3 parts of the builds can happen largely in parallel, a happy occurrence when building a machine for parallel computation. Andrew Fitzgibbon, Fitz, will be assembling the frame, which includes mounting the power supply and network switch. Jen Teal will be mounting main boards to mounting plates, which includes mounting the disk drive, LEDs, and power switch. Jamie Schwetman will be creating the bootable USB drive, using the USB drive to put the OS on the disk drive, and finally running the applications, which will show that the LittleFe unit is successfully running. The video will chart the assembly an individual can follow. You can certainly complete the build with just one person. However, it will proceed more rapidly if at least one more person assists. Be sure to pause and rewind as needed to be comfortable with each step of the assembly. The assembly process is very forgiving, provided you don't force or over-tighten anything, and you are careful with where and how you make electrical connections. Pause the video now so you can spread the parts out on a table. Make sure you have a pair of pliers, a regular-sized slotted screwdriver, regular-sized Phillips head screwdriver, a VGA monitor, a USB keyboard and mouse. You will also need an empty USB memory stick with at least 1 gig of memory. Please also have a computer and a copy of the BCCD ISO. That's the Bootable Cluster CD. You can get this ISO by going to bccd.net, clicking the download icon, and finally clicking the 64-bit version, whose file name will end with amd64.iso. On your table you will see 6 squarish boards that are the main boards. These are the heart of your LittleFe. A lot of what we will be doing is just connecting them, connecting power and connecting data. You will also see 3 large plates with strategically placed bends. These will be used to form the frame and will be connected together with the right metal bars and screws. Each end plate has a sticker you will be able to see from the outside when the frame is finally assembled. The plates with stickers are on the end plates, which will face out so that the stickers can be seen. One end will have an EAPF sticker and the other an Intel sticker. There are 2 different diameters of screws used, 3/8 and 3/4 inch of diameter 6/32, and 1/2 inch, 1 inch, and 1.5 inch of the 10/32 ones. Okay, we're back. Let's go over the parts you have laid out in front of you. You might have noticed that the kit of parts we're showing is not quite the same as the one you have in front of you. That's actually a very good thing, since the LittleFe reference design is constantly evolving. Until we have a functioning HDD, Hogwarts display device, Our videos will always be out of date. Please take a look at the LittleFe website, http://littlefe.net, for the latest kit of parts, written build instructions, and related material. This is the mounting and power supply section. These stages of assembly involve 4 hands. 2 can do it, but there is a careful balancing act coupled with a degree of dexterity required for success. Notice the equipment needed for this step. On the left side of the pad are 4 nylock locking nuts and 4 bolts. Next is a Phillips and finally a socket tool matching the nuts. Next is the power supply. The writing will be correctly oriented when mounted. Finally, the correct end plate, namely the one with the 4 holes corresponding to the grooves in the power supply. Notice the LittleFe sticker and what is in Fit's hand. Both will be pre-assembled, and both help establish orientation of the unit during assembly. We'll be attaching the bottom 2 nuts and bolts very loosely. The power supply will be nicely supported by them as we attach the last 2 nuts and bolts. Bolt heads are on the LittleFe sticker side. Nuts attach from what will be the inside. Now I will hold the nuts in place while Fitz screws the bolts into them. The plastic inserts in the nuts do a fabulous job of firmly connecting the power supply, even when being tossed from cargo hold to ground to baggage cart. And voila! The first step is complete with a Fitz trademark playful smirk. Notice the needed equipment, the other LittleFe stickered end plate and the middle plate. On the black pad you have 5 cable holders and their 5 long bolts and 5 locking nuts. Next to these you have 4 rows of lock washers and short screws, 1 row for each side rail, which has 2 holes on each end. Next are the 4 side rails, then the end plate with which we just finished, and finally the socket and screwdriver we used in the last step. The guide rails for the main boards have been pre-assembled for you. You don't want to disassemble them because correct alignment is sometimes fairly delicate. Each of the 4 side rails are marked so you can correctly align them to the middle and end plates. The slotted middle plate is just the main board's width from its equivalently slotted end plate. Fitz is pointing out the end of the sidebars that we will be attaching to the end plates. Notice the locking washer in Fitz's hand and then the screw. He will be attaching them to the sidebars by hand. Once the 2 are in, they can be tightened down. This is a general pattern. Start all the screws in a given assembly and then go back to tighten them. Never tighten one before they're all started. With the 4 sidebars attached to the power supply end plate, the next step is to attach the other end plate. Making sure to have the sticker side of the end plate out, I attach the remaining 8 washers and screws. We're now in the installing the main plate section. Fitz is pointing out the 4 pre-installed guide rails for the 6 mainboard plates. I'm placing the middle plate so it aligns with holes in the sidebars we'll be using for attaching it. As we've done previously, the bolt heads will be on the outside, nuts will be attached inside the frame. Notice the sequence of pieces. From the outside is bolt head, sidebar, cable guide, and nut. The bulge in the cable guide is on the power supply side of things. Fitz just gave the international finger wag symbol, indicating that the bolts should be just hand tightened for now. Similarly, a second cable guide is attached on the other side of the top of the middle plate, bulge still on the power supply side. With 2 fingers, Fitz subtly indicates we will have 2 cable guides on the bottom rail. Fitz points out the site of the first bit of asymmetry in construction. We will be placing a second cable guide on the bottom rail. But first we have to complete the 4th attachment of the middle without a cable guide. Yes, this is a second point of asymmetry. I am tilting the frame on its side to point out the sites where the 3 cable guides are attached and where the single cable guide is attached on the sidebar. It's okay to tighten down the 1 middle plate attachment without a cable guide. We have the 7 power cords with an end for screwing to the power supply and the other end for plugging into devices. The shorter cord is for the switch. The other 6 will power the main boards. We are now going to attach the power cords. Let's start with attaching them to the power supply. I am showing that the ends with white on them are positive and need to be screwed onto the positive terminal. This is a very important detail. We are now going to run the power cables sequentially through the cable guides. The first cable guide we take off is the lone one on the bottom side rail. Pop the cables into it, then reattach the cable guide to the sidebar. As we go, we will also be tightening the nuts on the bolts. Now unbolt the cable guide attached to the lower middle plate. Fitz is showing a new cable guide we will be attaching to the bottom of the middle plate. I am showing a bottom side view of cables as connected so far. Move the short power cable away from the others. Take the remaining 6, put them through another cable guide, and attach them to the next spot along the bottom of the middle plate. Now the switch is going to be mounted and used as a large cable guide. We are reorienting the frame so the top faces you. I am holding the power cables so they come up and over the middle plate. Fitz is showing the switch needs to be oriented so that its Ethernet slots face the bottom. It takes 2 hand-tightened screws to attach the network switch to the middle board and also be the final guide for the power cables. The socket tool does the final tightening to finish securing the switch. Fitz shrugs his shoulders, wondering if the main board plates will fit. Let's see. They fit! And Fitz is pleased enough with the situation. I am too. Big thumbs up from both of us. We are now going to install the Ethernet cables, which are the key element enabling LittleFe to be a cluster. Notice that Fitz has installed a group of 3 in the right side of the network switch, and then a corresponding group of 3 on the left side. We then pull the 2 groups of 3 through the center of the frame, so we are then set up to connect them to the main boards. Fitz reemphasizes the key fact that we have 2 groups of 3 cables. Before we actually connect to main boards, we need to connect the cables to the frame with, no surprise, cable guides. We each put our cables into cable guides. Fitz actually screws his into the frame, gesturing with the cable ends where they will ultimately be connected. Mounting the main boards to the main board plate section. There are 6 main boards to mount. Fitz is going to show you the assembly of just one, and a very important one it is. This will be the head node. It is the only one with a hard drive. On the left, you see a main board plate. On the black pad is a large Phillips screwdriver, the other socket tool, no blue on the handle, next a small Phillips screwdriver. Underneath these are the 4 nuts, 4 nylon spacers, 4 bolts, and 4 small hard drive screws. To the right of the black pad is the laptop hard drive and a main board. Above the hard drive and main board are the necessary cables, a power switch, a power LED, and an I/O activity LED. Fitz is indicating the orientation of the main board plate. Notice the 4 holes on the left, 2 in the middle and 2 on the right. The middle 2 holes on the left side and the ones next to them form a square that provide the mounting holes for the hard drive. Fitz is showing where it will be mounted on the back side of the plate. Make sure the top of the hard drive, the end with the connectors, is the end closest to the end of the plate. Use the small Phillips screwdriver to complete attaching the hard drive to the main board plate. Now, carefully flip the plate over and place the 4 nylon spacers over the remaining 4 holes in the corners of the plate. Now gently place a main board on top of the holes. There is only one correct orientation, so all holes line up. Fitz is now carefully putting the bolts through the holes in the main board so the bolt heads end up against the main board. Now comes a bit of a balancing act of securing the nuts to the bolts without turning the board over and spilling everything all over the table. Fitz is tightening each nut with a socket tool as he goes. It might be easier to first hand tighten all 4 nuts to the bolts before using the socket tool. You will see Fitz tightening the final nut and bolt, give 2 thumbs up, and reach for the cabling. First, put the SATA connector in the lower right corner. Both ends of the SATA connector are identical. The SATA connector carries the data to and from the hard drive. Now place the power connector for the hard drive. The black barrel connector attaches to the drive, and the white connector attaches to the main board, right next to the SATA connector. And now for the I/O LED, which attaches on the other side of the SATA connector. It identifies when the hard drive is being used. The main board LED is next, which is lit when the main board has power. It connects right next to the I/O LED. The power switch is in the lower right-hand corner. This is the first of the connections that will be done on each main board. The previous 3 are unique to the head node. Finally, the power switch is connected to the main board plate. Fitz has woven the LED cables and the power switch through the fins of the CPU heatsink. These will be routed under the main board, in the gap between it and the main board plate. Jen is going to be attaching the worker node main boards to their plates. Note that the power switch and LED have already been connected to the main board and been woven through to where the other connectors are. The black mat has the 4 spacers, bolts, and nuts to attach the main board to its plate in the exact same fashion as was done with the head node. Jen starts with the 4 white spacers. Notice the holes for where a hard drive would have been attached for the head node. Now the main board is set on the spacers so the holes line up. And note they only line up one way, with the orientation of the plate, so the hard drive holes are in the upper right relative to your viewing angle. The main board is positioned so its connections face high noon. Now, bolts are placed through the holes. Fitz is carefully raising the plate so Jen can connect the nuts one at a time. This works great with 2 people. With just one, you can carefully hand tighten all 4 and then tool tighten them one by one. As Jen gestures completion of the first worker board, you can see the other 4 magically complete themselves. Well, actually not, but Jen's completion of them was identical to that of the first she did. Jen is now going to slide each main board into the frame and connect Ethernet and power cables. She starts with the main board, identified by the black loop of the SATA cable and the hard drive to which it is attached. With the LittleFe frame oriented so the slots are nearest you, Jen places the head node in the leftmost slot. Notice all the connectors face up. It will take a gentle jostling to get the board seated correctly. There are 4 slots you have to navigate. The remaining 5 boards are installed in the same way, each with the connectors facing up. It should be no surprise that we can auto-magically advance to installation of the first board, which Jen gleefully places in the final slot, and with a David Copperfield flourish, the task is complete. Jen empowers the head node by attaching the nearest barrel power connector, smoothly and effortlessly connecting all 6. In the same way, she makes fast work of installing all the Ethernet cables, especially since there is only one NIC present in which to insert it. 3 cables come from one side and the other 3 from the other. Please do attach the shortest cable to the closest NIC. Jen's happy smile indicates pleasure with completion of the hardware assembly. Jamie is going to guide us through installing and testing the OS. We will be showing 2 different methods for creating a bootable USB drive, which will allow us to install our BCCD distro on a LittleFe. The first will guide the creation using a Windows machine. The second will produce the same results using a Linux machine. Let's start the Windows-based creation of a bootable USB drive. Make sure you have a USB drive with at least a gigabyte of storage. We will completely erase the drive, so make sure you first extract any needed data. Our first step is to get the current stable BCCD ISO from bccd.net. You can click either the orange Downloads tab or the green download arrow. They both take you to the same ISO repository. You'll notice there is a single 3.1 ISO version for 64-bit machines. There are both 32 and 64-bit ISOs for the 3.0 release. The fact that one ISO has an embedded AMD and the other an embedded Intel i386 is an unfortunate industry-wide naming convention that is also a red herring. Both ISOs will work with either AMD or Intel machines. The key thing is, one's for a 32-bit machine and one's for a 64-bit machine. Typically, we'll have ISOs for both 32 and 64-bit machines for every supported release. Let's click on the file name to get the desired ISO. Your browser will likely indicate the download has started. Please notice the MD5 in parentheses at the end of each line. We unfortunately omitted clicking it to download an MD5 checksum file. You will always want to do this and calculate an MD5 checksum on the file you've downloaded. If the two checksums don't match, you will need to refetch the ISOs. Transmission errors are typical for files of this size, in the gigabyte range. The awful, subtle, apparently intermittent errors they create are completely avoidable through use of checksums. Google is your friend, especially when locating the Windows tool to easily create the bootable USB. You can search for Universal USB Installer Download to see a plethora of potential possibilities. The one from Pendrive Linux is the tool of choice for us, so let's click on it. There are myriad spots on the page, each one demanding your attention. Pay them no heed and journey to the bottom of the page. You'll see there a button yielding the very exe file for the universal installer that we seek. We click on it to start the download. This one downloads almost instantly. Please get to the download directory for your browser. We happen to have several versions of the installer we've fetched while prepping this video. We select the latest, identical download. You'll likely have just one. Please click Yes to the Windows warning questioning the integrity of the download. In a likewise manner, click I agree on the Universal USB Installer License Agreement. Now for the fun stuff. There is a huge list of Linux distros you will discover by activating the Part 1 drop-down list. A little past midway down is the section for Other Distros, alphabetical. You will see the BCCD appearing here, and indeed, it is our own BCCD, which we will gleefully select. Please notice the link to the BCCD site, which now appears. It will indeed take us to the same BCCD homepage we visited a few minutes ago. We click on it now to show it takes us there. Step 2 is to select the BCCD ISO we earlier MD5 verified. We need to select the correct drive letter that corresponds to the USB drive we'll use for the bootable image. To be safe, we look at all our drives to know we have the right one. This will help us avoid the needless tragedy best left to Lear, Romeo, or Hamlet. We see that drive H is the one associated with the 1 gig USB drive we'll use. We can now confidently select the H drive as our desired destination. The pop-up shows the 5 dramatic, decisive steps that will be taken when you click Yes. And now the real work begins, which will last several minutes. We can now click Close to finish with the installation process, unmount our drive, and insert it into the USB slot on the head node's mainboard. And this completes the Windows installation. This is the Linux-based creation of a bootable USB drive with the BCCD ISO. We are going to download both the ISO and the build script from bccd.net. You will first need to become root, likely using the command sudo su dash. You will also need to insert the USB drive, which you will completely overwrite with the bccd ISO image. Let's make sure we know exactly what Linux device is associated with the USB drive. The output of the dmessage command will do this. If you type dmessage, the pipe symbol, and less, we will capture the output and be able to manipulate it. Press the G key without also pressing return. This will position us at the bottom of the output. Pressing capital U, capital S, capital B will then place the cursor where the letters USB last appeared in the output. This is the place we're looking for. Notice in our case, there are several lines with open bracket, SDB, close bracket. This is the info we're looking for. It might be open bracket, SDC, close bracket, but never open bracket, SDA, close bracket, because that's most likely your hard drive, and you don't want to overwrite it. Selecting a very wrong letter could overwrite your hard drive, which is virtually never a good thing to do. Press Q to leave the less command. Let's verify we have the right drive by checking its size. If the device was SDB for you, as it was for us, you'd type fdisk /dev/SDB. Type P at the fdisk command line to see the partition table. This shows we have a 1031 megabyte device, namely a 1 gig USB drive. Type Q to get out of fdisk. We are now going to use the wget command to fetch both the ISO image and the build script. Type wget http://cluster.erlm.edu/scripts/build_bootable_usb.sh. You can go to the bccd.net downloads area to see the available ISO images and the link to the build script. Right-clicking on them and copying the link address is what we did to get the necessary URLs for the wget command. Type wget http://cluster.erlm.edu/bccd-3.1.0-amd64.iso. This will take many minutes in fetching the 64-bit version of the bccd ISO. We can run the build script via the command sudo /build_bootable_usb.sh. This reveals we have two needed arguments, which we can and will provide to the script. We can now successfully run the build script by typing sudo /build_bootable_usb.sh /dev/SDB bccd-3.1.0-amd64.iso. Remember that dev/SDB is the device we discovered above when we use the dmessage command. This command will also run for several minutes, since it is also moving close to a gig of data. Please connect a keyboard and a VGA monitor to the head node. Make sure the power supply is set to the correct voltage for your neck of the woods, either 110 or 220 VAC. Setting it wrong can be devastating. Now you can plug LittleFe in. Note the snazzy bootable USB from the preceding step. She is inserting it in a USB slot on the head node mainboard, the one with the hard drive. Press the power switch to turn on the head node. The BIOS settings typically only need to be set once. All main boards need to have hyperthreading turned off, since high performance will come from the programmer managing the available cores via tools such as OpenMP and MPI. All worker nodes need to have BIOS settings so they do a boot across the Ethernet cable to the hard drive on the head node. The BIOS settings will refer to this as a local area network boot, or more simply, LAN boot, also called a PXE boot, PXE-BOOT. This is the only time you will have to connect a monitor to each main board VGA connector, along with a keyboard. Together, they will allow you to interact with the BIOS settings on each board. Press the power switch, and as the boards power on, repeatedly press the delete key on the keyboard. If you hear some beeping, you can stop pressing the delete key. The screen will display entering setup. No worries if you don't catch it. Just power off the board and start again. Information will display rapidly and disappear before you have a chance to read it, like this info about the USB devices. Don't worry, we'll let you know the places where things may need extra attention. Press the down arrow key twice to move the red bar down to Integrated Peripherals, which is the first item we'll be selecting by pressing the Enter key. We are now on the Integrated Peripherals page, from which we'll press the down arrow key, followed by pressing the Enter key to select Onboard Device function. We are now on the Onboard Device function page, from which we'll press the down arrow key, followed by pressing the Enter key to select Onboard LAN Boot ROM. This will give you a red options box. Press the down arrow key once, followed by pressing the Enter key to enable network booting. Notice we are back on the Onboard Device function page, which now shows Onboard LAN Boot ROM is enabled. Press the Escape key to return to the Integrated Peripherals page. And one more time to return to the main menu. Now press the up arrow key once, followed by pressing the Enter key to select the Advanced BIOS Features page. We are now on the Advanced BIOS Features page, from which we'll press the down arrow key, followed by pressing the Enter key to select the CPU Feature page. We are now on the CPU Feature page, from which we'll press the Enter key to select Hyper-Threading Technology. This will give you another red options box. Press the up arrow key once, followed by pressing the Enter key to disable hyperthreading. Notice we are back on the CPU Feature page, which now shows Hyper-Threading Technology is disabled. Press the Escape key to return to the Advanced BIOS Features page, and again to return to the main menu, which will save the changes and start the main board rebooting from the hard drive on the head node. This is why the head node is always the node that needs to be booted first. For now, please turn off the main board because we need to install the OS on the hard drive before we can succeed at booting any of the client nodes. Make sure you have placed the USB drive in one of the USB slots of the head node. You can now power up the head node to see this BCCD splash screen. Press Enter, and after a few moments, you will see one or more Tux penguins, hopefully corresponding to the number of cores you have on the head node. If you see more than you expect, it likely means you did not successfully disable hyperthreading in the preceding BIOS step. By the way, this boot up sequence from the USB drive will look a lot like booting up from the hard drive, for the simple reason it is the same boot sequence. We need to boot from USB to keep the hard drive completely free to be rewritten with all the good stuff from the USB drive. We are going to be seeing feedback from boot up of a Debian-based Linux distro. There will be pauses and lots of warnings and error messages flashing by. Don't worry, they are usually exactly what you want to see, except when they're not. You will generally just need to press the return key when the boot process is waiting for a response. I'll give you a heads up when these moments occur. Press return to set the password for the default user. namely the user bccd. Since you did not set a password here, you will not be prompted for a password when you try to run the system commands. For security reasons, however, you will not be able to log in remotely. So, if you want to log in remotely, you can use the recommended password of bccd, keeping it easy to remember. Username bccd, password bccd. If you are asked to enter your password again, it is just another press of the return key. Confirm the password with 2 presses of the return key. Press the return key to skip configuring an IP address for ETH0, which is the one and only NIC, network interface card. Later on, you can add a second NIC, the USB NIC, and redefine your network configuration to match the environment where your LittleFe will live. You may also see a prompt for no DHCP for ETH0, skip. Yes is the correct response. See the LittleFe website for more details on the network configuration process. This looks like another place where you need to interact, but the boot script is going to handle login for you, so be patient. In a successful boot, the final state will show a usage message followed by 2 command line windows. This was a successful boot, although run on a bccd version without the usage message. In one of the windows, type sudo space perl space /root liberate.pl space -- libdev space /dev/sda. This will run as the root user, also known as the superuser, which is necessary to fully access the hard drive. Liberate.pl is a script that will do this. It's written in the Perl programming language. If you earlier set a password for the bccd user, sudo will prompt for it now. Otherwise, the liberate script will just run. The script will now go through the series of steps required to boot directly from the head node hard drive, which, as might be expected, will take some time, about 4 minutes for the one we filmed. All 72 tests should pass. Note down any that do not, in case it ends up being significant, and proceed with the liberation. Once liberation completes, right-click on the desktop and select System, then Reboot, to reboot the system into the liberated mode of the bccd. We are now in the Boot from Hard Disk section, which is also where you will be every time you plug in your LittleFe and power on the head node. The boot sequence will be very similar to the USB boot, with the exception that the boot will proceed automatically to the 2 command line windows. Once again, we end up with our 2 command line windows. In one of the command line windows, type ls and press return to see what the bccd home directory looks like. There are several directories useful in showing parallel speedup, among other uses. We are going to test the success of our install by compiling and running the Galaxy simulation. These directories will also help students learn other fundamental parallel truths, such as communication overhead, domain and functional decomposition, and much, much more. So let's go to the Galaxy directory by typing cd space galaxy and return. Typing make space clean will clear out the directory, preparing for a fresh compile. You won't need to do that the first time, but now you know how to do it, if you need to. Make, by itself, will build everything, provided there is a well-written makefile, which Galaxy has. Typing mpi run space -np space 2 space -machine file space ~/.machines space /galaxy space 500 space 500 space 1000 truly has many interlocking parts. MPI run starts up a program that has been instrumented with the MPI library, which is quite true of our Galaxy program. NP defines how many processes will run, which is often the number of processors. Machine file
defines the available machines, namely the various LittleFe mainboards. You may need to run the command bccd-snarfhosts to create the machines file, which it conveniently calls machines, and which also conveniently ends up in bccd's home directory. Very soon now, there will be a different machines file corresponding to whatever MPI library you happen to use. OpenMPI, MPISH2, or perhaps LAM. The Galaxy program has set up a number of configuration options for itself. The 500, 500, and 1000 configure the Galaxy program for the specific simulation we're doing. You'll now see a window pop up showing 500 dots, which in our simulation represent galactic bodies, each with a solar mass of 500 and running for 1,000 million years, which ironically only takes us 8 seconds to render and display. On the left is a view from the top of our clockwise spinning galaxy. On the right is the very same galaxy as seen from the side. This concludes our building of our LittleFe, our installation of software, and our testing of that very same hardware and software.
You now have a working LittleFe. Congratulations! Please visit the curriculum section of the LittleFe website. You will find curricular materials ranging from self-paced units, lab assignments, homework assignments, and multi-week projects. Please consider extending or adding to this material and submit it to the LittleFe site for the use of others. This is essential for us to continue together doing what we're doing. The LittleFe site will also guide you to current related materials. We hope some viewers will also use it and the LittleFe website to design their own version of a LittleFe. It is a reference design for a computational cluster we have put under an open source copyright so we can all keep developing and extending it. And again, congratulations and welcome to the LittleFe community.